Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you like my videos because they are interesting and important to your studies, also please don't forget to subscribe. So here is series of problems on cables. Two equal loads P and are supported by a flexible cable ACDB as shown below. Determine the tensile forces T sub AC and tension CD of the cable if the span L is 9 meters and the sag D is 1.5 meters. Neglect the weight of the cable. So here is the given figure. I will solve this into two ways. One is by statics as shown. Because of symmetry, the vertical reaction because of the fact that the loads are vertical, the horizontal component of tensions at all points on the cable will be the same, and we will denote that by H. And the vertical component of reaction at or tension at A and B will be the same, equal to P by symmetry as shown. Then I cut portion AC, or simply the tension in AC is the resultant of this horizontal and vertical components. So the moment of the resultant about C is the sum of the moments of its components. But I'll just cut it and let's sum up moments about C equals 0, considering all forces to the left of that cutting section. So clockwise positive, counterclockwise positive rather, H times D equals P times L over 3. Substituting the value of D, which is 1.5, and L 9. So H times 1.5 equals P times 9 over 3. Therefore, H is 2P. Having known H 2P, the tension in AC is square root of H square plus P square. Tension in AC is square root of 2P quantity square plus P square. So therefore, tension in AC is square root of 5 times P. Likewise, we cut portion CD as shown. Then let's consider all forces to the left of that cutting section. So summation forces horizontal, obviously tension CD is equal to H. And since H equals 2P, so tension CD is 2P. Then for the second part, I'll apply the general cable theorem. So let's have the simply supported beam loaded with the same loading. And by symmetry again, the reaction at 1 is also P as well as at 2. Then by definition, the product of H and the vertical distance of the point to the imaginary chord, point on the cable to the imaginary chord. For that case, let us say point C or any point on this portion CD to the imaginary chord is D, and D is 1.5, is equal to the moment at the same point of the beam loaded with the same loading, so moment at C. And the moment at C is simply, we cut section C and we consider the force to the left of that cutting section, so the moment at C is P times 3. So H times 1.5, H times D equals moment at C, which is P times 3. So H is equal to 2P, and the same calculation as before, tension AC would be square root of 2P quantity square plus P square, so it is square root of 5P. And tension CD by summing up forces horizontal would be 2P also. So after we solve for H, which is 2P, the rest of the solution will be similar to the first part. What is important is I applied the general cable theorem in computing the value of H in a different way, but the result is the same. The formula is also the same. On the string ACEDB are hung three equal weights W symmetrically placed with respect to the vertical line through the midpoint E as shown below. Determine the value of the angle theta. So here is the angle theta. So take note that these hang equal weights W are symmetrically positioned. Then we conclude that the horizontal and vertical components of reactions at A and B will be equal because of the loadings. The horizontal component of tension is, we will designate it as H. The vertical component of tension at A and B will be 3W divided by 2, or 1.5 W, as shown in the figure. So I cut portion C, then summation forces horizontal equals 0. So TCE cosine of theta equals H. Call that equation 1. TCE cosine theta, rightward component, equals H. Summation forces vertical equals 0. 1.5 W minus W minus TCE sine theta equals 0. So TCE sine theta equals 0.5 of W. Then we consider the free body diagram of point A as shown, and denote the tension in AC as TAC. Summation forces horizontal vertical equals 0. 1.5 W minus TAC sine of 60 degrees equals 0. So TAC is equal to square root of 3 of W. Then summation forces horizontal equals 0. TAC cosine 60 equals H. And since TAC is square root of 3W, substituting, then we can now compute H in terms of W. H is equal to 0.5 square root of 3W. So equation 2 divided by equation 1, TCE sine theta divided by TCE cosine theta equals 0.5 W over H, and H is 0.5 square root of 3W. So 0.5 W over H, this is H, 0.5 square root of 3W. Cancel out W, cancel out TCE. So tangent theta equals 1 over square root of 3. So from there, we can now solve theta. Theta equals 30 degrees. So that's it for this problem. Two vertical masts AB and CD are guided by the wires BF and DG in the same vertical plane and connected by a cable BD of length L from the middle point E, of which suspended a load W. Find the tensile force in each of the two guy wires BF and DG if the load W is 500 newtons, the length L of BD is 6 meters, and the sag D 30 cm. 30 cm is 0.3 meter. So this is 0.3 meter. BD is 6 meters, therefore half of BD is 3 meters. So for the solution, I'll only present one solution here. So let's consider the free body diagram of joint E. We will call the tension in BE and DE since they are equal as T1 as shown. So summation forces vertical equals 0. 2 times T1, 2 times the vertical component of T1. The vertical component of T1 is D, which is 0.3, divided by length of BE, which is square root of 3 square plus 0.3 square, then equals W. So 2 times T1, vertical component 0.3 over square root of 3 square plus 0.3 square equals W. So T sub 1 is equal to 5.025 of W. Then we draw free body diagram or isolate joint B. Draw the FBD. So this is T1, then vertical reaction, then this is the tension in BF, which is expected equal to tension in DG also. We will call it T. Then summation forces horizontal, T1 times 3 over square root of 3 square plus 0.3 square equals T sine of 30 degrees, or minus T sine 30 degrees equals 0. Then T is equal to 1.990 of T1. Substitute the value of T1, which is this, and substitute the value of W, which is 500 newtons. So T is 1.990 of 5.025 times 500. So T equals 5,000 newtons. Therefore, tension in BF equals tension in DG equals 5,000 newtons. Determine the angles theta 2 and theta 3 and the force in each cable segment if theta 1 is 50 degrees. So here's the given figure. I'll present two solutions here, one by statics and the other by the general cable theorem. So we will call the horizontal component tensions because the loads are vertical as H, as shown in the figure. We'll call this is the imaginary chord, call this YB, Y sub C, then HB, then this is H sub C. Then the horizontal component of tension H, vertical component of tension VA, and V sub D. So summation of moments about D equals 0. This is the tension in AB, the resultant between H and V sub A, the components at A, components of the reaction at A. And the tension in CD is the resultant of this rightward horizontal component H and V sub D. So summation moment about D equals 0. The vertical component is T sub AB sine 50 degrees because theta 1 is given, times 26 minus H times 10 minus H, which is T sub AB cosine of 50 degrees times 10. So that's the horizontal component. Then minus 12 times 20 minus 18 times 12 equals 0. So from here, we can solve tension in AB, which is also expected the maximum tension in the cable. So tension AB is equal to 33.8 kilonewtons. Having found tension AB, we can compute VA and H actually, and we can also compute this vertical distance. So H is tension AB cosine of 50 degrees. H is equal to 21.726, the horizontal component of tension at any point on the cable, or the horizontal component of tension to any cable segment. And the vertical component is tension AB sine of 50 degrees, 33.8 sine of 50 degrees, so it is equal to 25.892 kilonewtons. Then we'll call this D sub B, this one D sub C. Tangent of 50 degrees equals D sub B over 6. Therefore, D sub B is equal to 6 tangent of 50 degrees. Then considering ABC, I cut this portion BC here and let's sum up moments about C. Considering forces to the left of that cutting section, so summation moment about C equals 0. Then we have 25.892 V sub A times 14 minus H, which is 21.726 times D sub C minus 12 times 8 minus 12 times 8, that is 8, equals 0. So from there, we can solve D sub C. D sub C equals 12.266 meters. Having found D sub C, we can compute theta 2. Imagine this right triangle here. Tangent of theta 2 is this distance. This distance is D sub C minus D sub B, then divided by 8. So tangent theta 2 is distance C, 12.266 minus distance B, 6 tangent of 50 degrees, divided by 8 in this imaginary right triangle. So theta 2 is equal to 32.60 degrees. Then the tension in BC can be found. The horizontal component of tension BC, TBC cosine theta 2 equals H. So tension BC cosine of 32.6 degrees equals 21.726 H. So tension BC can now be computed. It is equal to 25.79 kilonewtons. Then tangent of theta 3 equals opposite. Imagine this right triangle here. This opposite side of this imaginary right triangle is D sub C minus 10, then divided by horizontal distance 12. Tangent theta 3 is equal to D sub C, which is 12.266 minus 10 divided by 12. So theta 3 can now be computed. It is equal to 10.69 degrees. Then tension CD cosine of 10.69 degrees is H. So tension CD cosine of 10.69 degrees equals H, 21.726. So tension CD can now be computed. It is equal to 22.11 kilonewtons. Then for the second solution, let's have a beam loaded with the same loadings. So 12 kilonewtons, 18 kilonewtons, 6 meters from this support, then 8, then 12. Then let's compute for the reactions. Before that, let's have YB as to 6 equals YC as to 14 equals 10 as to 26 to solve for YB and Y sub C. YB is equal to 30 over 13 meters. Y sub C is equal to 70 over 13 meters. So let's, you have to memorize this because the extension of the solution will be on the next slide. Then R1 and R2, summation moment about zero point 0.2 equals 0. So R1 times 26 minus 12 times 20 minus 18 times 12 equals 0. So R1 is equal to 228 over 13 kilonewtons as shown. Then R2 equals 12 plus 18 minus R1, or summation versus Y, R1 plus R2 equals 12 plus 18. So R2 therefore is 12 plus 18 minus R1. So R1 is equal to R2 is equal to 162 over 13 kilonewtons. So familiar with these values, let's have them copied on the next slide. So recall from the preceding slides, these are the this is the figure. Then for the beam, then the values of D sub B, 6 tangent of 50 degrees, YB which is equal to 30 over 13 meters, and Y sub C 70 over 13 meters. Then R1 is already here and R2 also. Then let's solve for HB. It is equal to D sub B, 6 tangent of 50 degrees minus YB which is 30 over 13. So HB is equal to 4.843 meters. Then from the general cable theorem, the product of the horizontal component of tension and the vertical distance of this point on the cable to the imaginary cord, which is HB, is equal to the moment at the same point on the beam loaded with the same loadings. So it is moment about B. At the moment about B, if we cut section B, considering the force to the left, is only 228 over 13 times 6. So again, H times HB equals moment at B on the beam. So H times 4.843 equals the moment about B is 228 over 13 times 6. Solving for H is 21.728 kilonewtons, which is slightly almost the same as before, 21.726 before. Then for vertical reaction, we sum up moments about D equals 0, V sub A times 26 minus H, which is 21.728 times 10 minus 12 times 20 minus 18 times 12 equals 0. So vertical component of reaction at A is 25.895 kilonewtons. So the tension in AB can now be computed, square root of 21.728 square plus 25.895 square. So tension AB is equal to 33.8 kilonewtons, just like before. Then let's solve for H sub C. Again, H times H sub C is equal to the moment about C. The moment about C is either 228 over 13 times 14 minus 12 times 8, or the easier way, R2 162 over 13 times 12. So H times H sub C equals moment about C. H, which is already found, 21.728 times H sub C equals 228 over 13 times 14 minus 12 times 8, or it is equal to 162 over 13 times 12. So either way, you use this, the right side value is the same, so we can now compute H sub C. H sub C is equal to 6.882 meters. Having found H sub C, we can now compute D sub C, which is H sub C plus YC. So D sub C is 70 over 13 y sub c plus 8 sub c, which is 6.882. So d sub c is equal to 12.267 meters. We can now compute theta 2, tangent theta 2 equals d sub c 12.267 minus d sub b 6 tangent 50 all over 8. So tangent theta 2 equals 12.267 minus 6 tangent 50 degrees over 8. So theta 2 equals 32.60 degrees, just like before. Then having found um, theta 2, we can compute tension BC. Tension BC cosine of theta 2 equals H, which is 21.728. So TBC cosine 32.60 degrees equals 21.728. So tension BC is equal to 25.79 kilonewtons. So it's the same. Then tangent theta 3 is equal to d sub c, which is 12.267 minus 10 divided by 12. Tangent theta 3 equals 12.267 minus 10, this vertical distance, divided by 12. So theta 3 is equal to 10.70 degrees. So it was 10.69, so that's acceptable. Then tension CD cosine of 10.70 degrees equals H, which is 21.728. So tension CD is equal to 22.11 kilonewtons, just like before. So that's it for this problem. I presented two ways, and in your case, you may just present one way, unless otherwise you are instructed to solve it into two ways. Determine the reaction components, cable sag, D sub B, and the maximum tensile force in the cable. So in this problem, I again present two solutions, one by statics and the other one by the application of the general cable theorem, because the loads are vertical. So we will denote the horizontal component of tension as H as shown, then the vertical components as V sub A and V sub D. So considering the whole system, summation moment about A equals 0, counterclockwise positive, so V sub D times 40 minus H times 2 minus 5,000 kilograms times 9.81 divided by 1,000 to convert it to kilonewtons times 10, 5,000 times 9.81 divided by 1,000 to make it kilonewtons times 10 minus 6,000 times 9.81 over 1,000 times 25 equals 0. So formulating the first equation, 40 V sub D minus 2H equals 1962. Call that equation 1. Then we have tension CD here. The moment of the resultant equals the sum of the moments about it of its components about C, or we cut CD, then we sum up moments about C considering forces only to the right of that cutting section. So only V sub D and H will be involved because T sub CD passes through C. So from the figure, V sub D times 15, summation moment about C, minus H times 6 equals 0. So the second equation, 15 V sub D minus 6H equals 0. Equation 2, solving these two equations simultaneously, we have V sub D equals 56.057 kilonewtons, H equals 140.140 kilonewtons. These are the reaction components at D. The reaction components at A would be H 140.140 kilonewtons to the left and V sub A by summation forces Y. So T max therefore is square root of 140.140 square plus 56.057 square. It is expected as tension CD because D is the highest point in this cable here. The maximum tension is expected to be at the highest point and farthest. So T max equals 150.9 kilonewtons. Then for VA, summation forces Y, V sub A plus 56.057 V sub D equals 5,000 plus 6,000, so 11,000 kilograms times 9.81 divided by 1,000. So 5,000 plus 6,000 times 9.81 over 1,000. V sub A is equal to 51.853 kilonewtons. So reaction components at A would be 51.853 kilonewtons at A and H 140.143 kilonewtons. So 51.853 times 10 minus 1 summation moment about B equals 0 to solve for D sub B. So V sub A times 10, imagine this is cut, or by Varignon's theorem, the moment of the resultant about B, which is 0, is the sum of the moments of its components. So V sub A times 10, this is V sub A 51.853, then times 10 minus H, the distance here is D sub B minus 2. So this distance of H from B is D sub B minus 2 equals 0. So solving for D sub B is equal to 5.7 meters. Then having found D sub B, we have the second solution. By the way, reaction components at A would be 51.853 vertical, H 140.140 horizontal to the left kilonewtons. Then we have here a simple beam. Then we have to solve for R1 summation moment about to equal 0. R1 times 40 minus or equals 58.86 times 15 plus 49.05 times 30. So R1 equals 58.86 kilonewtons. So call this Y sub C, this small value here. Then this distance as Y sub B, and this distance as H sub C. Y sub B, then this distance as H sub B, as indicated in the figure. By similar triangles, 2 meters as to 40 equals YB as to 30 equals YC as to 15. So YB is equal to 1.5 meters, YC equals 0.75 meter. Then by definition, HB, H sub C can be computed. H sub C can be computed first. H sub C is 6 minus YC. 6 minus 0.75 is 5.25 meters. Applying the general cable theorem, the product of the horizontal component of tension and the vertical distance of point C to the imaginary chord, H sub C is equal to the moment at C on the beam. And the moment at C is either R1 times 25 minus 49.05 times 15 or R2 times 15, the simpler way. But I'll just consider forces to the left of the section. So R1 times 25 minus 49.05 times 15 for the moment at C. So H times H sub C equals moment about point C on the beam. H is unknown yet for the second solution, then times H sub C, which is 5.25, equals R1, which is 58.86 times 25 minus 49.05 times 15. So that's the moment at point C considering forces to the left. So H can now be computed, and it is equal to 140.140, just like this kilonewtons. So having found H, then we can compute V sub D. V sub D would be from this equation, summation moment C, V sub D times 15 equals H times 6. So substitute here, then we can compute V sub D 56.057 kilonewtons. So T max automatic square root of 140.140 square plus 56.057 square, 150.9 kilonewtons. Then for D sub B, so H times H sub B equals moment at B. So H has been found. 140.143 times HB equals moment at B is R1 times 10. So 58.86 times 10. So HB is equal to 4.2 meters. Then finally, D sub B is YB plus HB. D sub E is YB 1.5 plus HB 4.2. So D sub E is 5.7, just like that. So that's it for this problem.